Hello, we are studying Chapter 9, Intro to Differential Equations, and today we're going to go over the mixing problems, which might set up a separable differential equation or it might set up a first-order linear differential equation. So first it might just describe the model that we set up. You know, a typical mixing problem usually involves a tank of a fixed capacity. It's filled with a thoroughly mixed solution of substance. In this case, we're going to be looking at salt. It could be alcohol, it could be tea, it could be anything, or you could even consider these mixture problems in terms of air, like how much carbon dioxide is in the air. But anyway, so if we're given a tank with a fixed capacity, and that's a fixed volume, and it's kept thoroughly mixed, and we have a certain substance in there, such as salt, a solution of a given concentration is usually going to be the amount of that substance, like the amount of salt per volume. So we might have kilograms per liter or pounds per gallon, that kind of thing. So a solution of a given concentration enters the tank at a fixed rate, and the mixture, just think you're like a witch and stirring your brew. It's kept thoroughly stirred so that you have uniform concentration throughout. But then you also have a hole, and your liquid will leave at a fixed rate. And that might differ from the entering rate. So first, we usually want to let y of t equal the amount of the substance. And in this particular example that you see here, we'll say the amount of salt in the tank at time t. Good? So if that is the case, then we know that y prime of t is the rate at which the substance is being added minus the rate at which it is being removed. So then we would say dy dt is your rate of salt added minus your rate of salt removed. Rate in minus rate out. And how would we come up with that if we're going to say, and in this case we've got the amount of salt is in pounds. So, and we have that the time that we see in terms of rates of change, we see that it's in minutes. And so we know over here that dy dt is going to be in terms of pounds per minute. And again, concentration of a substance in a volume or in a three-dimensional space. So you can consider air and particles in the air in terms of concentration. We would have, if we look at concentration times our rate, we would have pounds per, and in this case our volume is measured in gallons, but then our rate would be gallons per minute. And you can see from that dimensional analysis we can cancel our gallons and we would get pounds per minute, right? And that, again, would line up with our dy dt. So you can see that this is a good model for the mixing procedure. Usually, we know exactly what the concentration coming in to the tank is, but imagine if we are stirring the pot and we're changing the concentration as we're adding liquid in, and while we're changing it, it is dynamically changing the concentration if we're adding something with a different concentration. So what's difficult is on the right-hand side, or in the rate out, we want the concentration out, and that's usually what we need to find an expression for. That's the hardest part of setting up the equation, but the rate out is usually given as well. So normally the concentration is given coming in. Normally the rate coming in is usually given in your problem, and it's just a matter of figuring out what the concentration out would be. So again, we go with the definition of concentration. It's the amount of the substance over the total volume. So if at time t we have the amount is going to be y of t. And at any given time, we want to go to the initial amount in the tank. So we see our initial volume of the liquid at the beginning, because we'll always start with that. But we also want to add what's coming in and take out what's going out, because that will tell us how much volume we have at time t. So it's the amount at time t, and at time t, the volume, right? And how do we have that come in? We know that that's going to be rate times time, and so it would be the rate in, and our rate in and our time would be t. So we would have something like 4 times t coming in, if it was coming in at 4 gallons per minute. So let's go ahead and do this problem, and I'm going to recopy it so that we have it set up down below. All right, so we'll do that again here. All right, so in setting up, we are going to say let y of t equal the amount of salt in the tank at time t. Good. We also see at the very beginning, before we turn on any faucets and before we start draining the tank, we have 40 pounds of salt that is dissolved in the tank. So that tells me that my initial conditions are going to be at time t equal to 0, y of 0 is going to equal 40 pounds. And that's where you can use that value from your problem. Next, we set up our model, and we know that dy dt is going to be rate in minus your rate out. And my rate in is going to be my concentration in times my rate in minus my concentration out times my rate out. Good. And I see from this example a brine, which is just salty water, containing 2 pounds per gallon of salt runs into the tank at a rate of 4 gallons per minute. So the concentration is going to be 2, and the rate in is going to be 4. Minus our concentration out is going to be y over, and I know I have plus 4 times t because that's the amount that's being added. But what's my rate out? My rate out, it says the mixture is kept uniform by stirring and flows out of the tank at the rate of 3 gallons per minute. So we want to write 3 here, but then we also want to subtract 3t, because that's going to give us our total volume at any time t in the tank as it's kept mixing. So that is my dy dt equal to, and if I go ahead and simplify, I get 8 minus 3 over 100 plus t times y. And now I have a first order differential equation. We're going to go forth and use the linear differential equation process to solve. So first part of that is to put our equation in standard form. And putting that in standard form, I have dy dt plus 3 over 100 plus t times y equal to 8. Next step, my integrating factor is going to be e to the integral of p of t dt, and our p of t is the plus 3 over 100 plus t. So in calculating that, I end up with e to the 3 times 1 over 100 plus t dt. That gives me e to the 3 times the ln of 100 plus t. I'm going to put that 3 using log properties as an exponent inside the ln because I want to simplify my integrating factor. And so I have 100t plus t cubed. And now I have e to the ln, which are inverse processes of each other. And so my integrating factor here is going to be 100 plus t cubed. In our next step in solving our linear differential equation, we multiply both sides of our equation by the integrating factor. So we'll be doing 100 plus t cubed times dy dt plus 3 over 100 plus t times y equal to 8 times 100 plus t cubed. I next transform the right-hand side into the derivative with respect to t of our integrating factor, which is 100 plus t cubed, times y. And on the right-hand side, I simplify, which I don't need to do because it's already simplified. Our next step is to integrate both sides. So I'm going to integrate the left, and I'm also going to integrate the y with respect to t. Derivatives and integrals are inverse processes of each other, so the left-hand side transforms to 100 plus t cubed times y, and the right-hand side with a u substitution of 100 plus t, I would end up with an 8 times u cubed du, because our du here would just be dt. And in integrating, I would end up with 8 times u to the 4th over 4, and 8 divided by 4 is 2. And in back substituting, I would end up with 100 plus t to the 4th, and I have plus c. Next, in solving for y, I would end up with y is equal to 2 times 100 plus t to the 4th plus c, all divided by 100 plus t to the 3rd power. Good. That is my general solution. So now I can use that as a family of functions, but now I want to, as a general solution to the mixing process here, but now I want to return to the initial conditions, and my initial values were that at time t equal to 0, I had 40 pounds of salt in the tank. So I'm going to use that when t is equal to 0, y is equal to 40, and I'm going to solve for c to find the particular solution. And so here I go. I have 40 on this side, and I'm going to go 2 times 100 plus 0 is going to give me 100 to the 4th power plus c over 100 plus 0, and I'll have 100 cubed. Good. Next, if I were to split this up, I do end up with 40 equal to 200 plus c over 100 cubed. I can move the 200 to the other side and get a negative 160 equal to c over 100 cubed. And then in multiplying on both sides, I get a negative 160 times 100 cubed equal to my c. So my final particular solution, my y of t, which is my particular solution, is going to be 2 times 100 plus t to the 4th power minus 160 times 100 cubed, which is a pretty small or pretty big number. I'll just leave it in that form, over 100 plus t cubed. So this is my particular solution, and now at any time I can say, well, how much salt is in the tank after 10 minutes, or how much salt is in the tank after an hour, and I will be able to tell you as much. However, knowing from the, you might have other restraints or other range of possible values of T, knowing that the amount entering the tank is 4 gallons per minute, and the amount leaving the tank is 3 gallons per minute. So eventually, dependent upon the size of your tank, you will end up with an overflowing scenario, but it's still going to, and then you'll have to modify, like how fast is it slipping out over the top. Good. So I hope this is clear in setting up that process and useful.